I'm trying to share my screen. Does it work?
Yes, and I will briefly introduce you. So the third speaker for today is Professor Dr. Daniel Karthe. From beginning of November now, he represents the United Nations University, and he came back to Germany after being a professor in Mongolia, in German Mongolian University. And also it's a pleasure to always to introduce Daniel on some sort of Moscow State University seminars or lectures, as far as he's a very big friend also for our department with long mutual history of very big collaborative research. And his talk will go to the area where many scientists meet together, to the Selenga Basin. So, and I give a floor to Daniel. Please, very welcome, and thanks you find time to make a lecture here.
Thank you very much for the introduction, Sergey. I think we now look back to 10 years of collaboration. My topic today will be water quality problems in the Mongolian subbasins of the Selenga, a Nexus perspective. And very first, I would briefly like to introduce myself. I'm currently the head of the research program, Resource Nexus for Regions in Transformation, at the United Nations University, which has campuses in several different countries, including Germany, where our focus is on integrated management of matter fluxes and of resources. Previously, I served for the German Mongolian Institute for Resources and Technology for 3.5 years, and prior to that, 7 years at the Helmholtz Center for Environmental Research. And some of the work that I'm presenting today actually goes back to the work with these two institutions as well. So very firstly, I would like to introduce you to the resource nexus concept, which is a fundamental concept that underlies all the work that we do at UNU Flores, my institute. I will give a very brief introduction into the Selenga River, Lake Baikal Basin. And then in a second larger chapter, I will take a look at how to apply the resource nexus for the basin of the Selenga and Lake Baikal. I will firstly give a short introduction into mining and in the upper Selenga Basin. I will then look at raw materials, water and soil, and connections between these elements, and then in a second step, look at food security, water and soil, for which you will see there will then also be some links to the previous considerations looking at raw materials. Finally, I will summarize some of the findings and discuss some key linkages. So firstly, the resource nexus is an approach to looking at multiple environmental resources, looking at the interrelations between different resources, the interdependencies between environmental resources, but also their transitions and fluxes across spatial scales and between compartments. And basically, the resource nexus considers environmental resources as a complex system where we need to consider different resources, not in isolation, but in an integrated way. And the resource nexus concept was actually first introduced in the year 2011 at the so-called Bonn Nexus conference. And back then, the key focus was actually on water, food, and energy security. And the concept of the resource nexus during the past 10 years has evolved, adding additional perspectives to the nexus. One example is the so-called water, waste, and soil nexus. And today, preferably, we speak of the resource nexus that is even more integrated, looking at an integration of biotic and abiotic resources, but also at waste and energy. Now, when we look at the resource nexus, here you can see the elements water, food, energy, materials, and land resources. these different nexus elements are connected to each other in multiple ways. And these linkages are actually strongly connected to the Sustainable Development Goals that were formulated by the United Nations. So if we look, for example, at the connection between water and food here, you can see that obviously it would be the SDG number 2, zero hunger. But we can see also that there would be connections to other SDGs, such as SDG 11, sustainable cities and communities, or for example, SDG 15, life on land. Now, in this talk, we will be taking a look at the Selenga River, Lake Baikal Basin. And as I think as Russians, you're all familiar that Lake Baikal is the world's oldest and by volume the largest freshwater lake, the deepest freshwater lake. And when we look at this lake, we can basically say that it depends a lot on what happens in the basin of the Selenga River. So in the black outline on the map, you can see the basin of Lake Baikal, and most of that is basically the network of the Selenga River and its tributaries. In the end, between 50 and 60% of the surface water influx into Baikal depend on what is happening in the Selenga River basin. Now, when we look at Lake Baikal, it's a lake that has a global relevance. It's recognized, for example, as a World Heritage Site. And one very important part of this lake, or of the Selenga Baikal Basin, is formed by the Selenga Delta, which is one of the world's largest inland deltas, and it's a wetland of international relevance. So the Selenga Delta is, for example, included on the international Ramsar Convention, which deals with the protection of wetlands of international importance. So basically what happens in the Selenga does not only affect Lake Baikal, but also the Selenga Delta. Now, we will take a look at the application of the resource nexus concept for the Selenga River. And the focus here will be the interlinkages between water resources and water quality as a central element, and its connections firstly to the raw material sector, which is of course a consumer, but also a polluter of water. We will look at the connections to soil security and to food security. Now, when we look at the mining sector in Mongolia, we can basically state that this sector is of a very significant economic importance. The mining sector contributes about 20% to Mongolia's gross domestic product, about 20% of the government budget. If we look at foreign direct investment, about 73% of the investments are related to the mining sector, and about 90% of Mongolia's exports are produced in the mining sector. In the picture that you can see on the bottom of this page, you can see an example of one of those mining sites, the copper molybdenum mine, which operates in the city of Erdenet, that in a few minutes we will take a closer look at. Now, when we think about raw materials extraction, and we now focus on the Mongolian part of the Selenga River Basin, we can see that there is one region that is basically located between the national capital of Ulaanbaatar, a little bit to the west of it and north of it, where we find these red dots which mark mining sites. And basically, when we look at these mining sites in the Mongolian part of the basin, the most important commodities would be copper, molybdenum, which I already mentioned for the city of Erdenet here. But there is also some coal mining activities. And quite some gold mining that is located mostly between Ulaanbaatar city and the Russian border. Raw materials extraction also takes place in the Russian part of the basin, where molybdenum, tungsten, and gold are the most important commodities. I will now focus on the Mongolian part. So when looking at the upper Selenga River basin, basically we can state that mining is firstly a very major water user. At least 80 million cubic meters of water per year are used for mining. Some estimates go far higher and state that it's 200 or 300 million cubic meters per year. And we can state that approximately 7 cubic meters of water are used for handling and processing 1 cubic meter of ore. So the mining sector is a very major water consumer, but also an important polluter of water and soils. And it is a very important cause of erosion and land degradation. When looking at mining-associated pollution in the rivers of northern Mongolia, firstly, we can say that increased turbidity is a general consequence of mining operations. So there is a sediment input into the river system that is related to various mining activities. But there are also several trace elements which have been found to occur in higher concentrations downstream of mining sites. And this includes a very long list of elements, including aluminium, arsenic, cadmium, chromium, copper, iron, manganese, molybdenum, nickel, lead, selenium, uranium, vanadium, zinc. So we can see it's a very long list of elements, and some of these elements are actually very toxic and of a great importance for the aquatic ecosystem. Now, when looking at pollution that is caused by mining operations, on this picture here, we can see soil pollution along the Tool River, which is one of the tributaries that leads towards the Orkhon and then ultimately the Selenga River in Mongolia. And we can see different elements here, for example, arsenic, iron, zinc, lead, strontium, cadmium. And what is notable here is that several of these elements, when we look at soils, are found in high concentrations in soils in close proximity to the rivers. And this is actually very often related to mining activities. In the case of the Tool River, this is chiefly gold mining in a region called Sama. Now, when we think about soil pollution and water pollution, basically we can say that there is a relatively strong linkage between these two. When we look at the sediments that we find in the river system, some colleagues of mine did research on the identification of fine sediment sources using geochemical and isotope-based fingerprinting techniques. And depending on the location in the river network, basically 50 to 90% approximately of the sediments, the fine sediments found in the river system originated from the river banks. And this basically tells us that river pollution from mining is a very real threat, particularly when mining operations take place very close to the river. And this is something that we very often find. We will see some examples soon. Now, when we look at the transport of elements in the river system, we can state that there are some elements which are predominantly transported in suspended form, whereas others are predominantly transported in dissolved form. Example for problematic elements that are transported in the suspended form would, for example, be nickel or lead. But there are other elements such as, for example, arsenic, cadmium, chromium, molybdenum, uranium, which are predominantly transported in the dissolved form. If you look at the table that you can see on the top of this slide, you can see different elements and the relative share of the element that is transported in suspended form during high water and low water periods. So for example, if you look at the first one, you can see here the element of iron, 98% during high water periods would be transported in the suspended fraction. If we look by contrast to here a low water period, that would be 67%. And when looking here at the bottom at areas with a high anthropogenic impact, those relative percentages are a little bit different. We can see, for example, for iron, that it's always transported very predominantly in suspended form. So basically, we can see that there is a difference between different elements regarding their main mode of transportation in the river system. But there is also a very significant impact that the hydrology has on this transport. So when we look at the mode of trace element transport, in this case at the Mongolian Russian border where the Selenga crosses the border, we can see that there is a very different picture for flood period shown on the left side of the slide and a low water period on the right side. So we can see that during the flood period, there is for many elements a dominance of suspended transport, which is probably a sign that they were rather newly mobilized and entered the river system. Whereas during a low water period, this picture looks rather different, and for most fraction is the dominant one. So it's the fractions of the two suspended and dissolved the hydrology. Suspended sediment concentrations in the basin of the river basin, we can see that the average suspended sediment concentrations in some regions, which are marked in the dark red colors, would exceed 250 milligrams per liter, whereas in other parts of the basin, they would be far lower. And when we think about the sources of these suspended sediments, we can see that the largest mining areas that we can see here, the largest ones which are located close or just next find the highest suspended sediment of Samar that I mentioned already before, a gold mining region that is found proximity to the true river mining, which is actually taking place within the river banks. You can see on the right side a picture that was a part of a news report in Mongolia in 2018. In this case, actually, a gold mining company that claimed to have an ecological process. So they call themselves Eco Gold. And if we see that the river is in very close proximity to the region that they are here preparing for the gold mining and preparing for flooding, we can see that even today, even though it's in theory illegal to have mining operations within the riverine floodplains, we can see that this is actually still reality. Now, when we look at the pollution of the river system, here we take a look at one specific element, namely arsenic, and we see in this picture here the enrichment factors in relation to the standards for Mongolia and Russia. And what we can see here is that it's actually two mining areas. This one here would be the Zama gold mining area. This one here would be the Erdenet copper molybdenum mining area. And we can see that these are the two regions where, for the element of arsenic, we find the greatest levels of enrichment. And the extreme values we can see here are particularly notable for the Zama region, where it's 82 times the levels, the standard levels. Now we look at the second important mining region, namely the Erdenet copper molybdenum mine. And when you look at this map, you can see here the location of the mine itself. You can see here the city of Erdenet. And on the top of the picture, you can see a tailing pond into which many of the mine tailings are deposited. One problem that very often occurs is that parts of this tailing pond dry up, and a phenomenon that is locally referred to as white dust happens. These are small dust particles which are formed after parts of the pond have desiccated, and the wind then begins to transport these fine dust particles. We are in a region where the dominant wind direction is winds coming from westerly or northwesterly direction. And basically this means that when we look here at this tailing pond, there is a significant risk that material that is here, if this dust becomes mobilized, it can be moved towards the Hangal River, which in the end flows into the Orkhon and then the Selenga River. And when we look at the soils, but also the Hangal River, several priority substances could be identified. They include arsenic, which is often contained in the ores, which also contain the copper and molybdenum. So there is arsenic also in the mine tailings, from where it can then be mobilized. We find, not surprisingly, copper and molybdenum in elevated concentrations in the soils, but also a few other elements that are found in elevated concentrations. Now, when looking at water pollution, if we detect water pollution with a certain element, of course, we need, initially, we need to assume that there can be different origins. The pollution may be one that is mining related, but trace elements could also be of a simple geogenic source. So it's very much relevant to compare the situation to the regional natural background levels to really reveal if the pollution is actually related to mining impacts. Something that we also find rather often in the Mongolian part of the Selenga River Basin is that some mines would close down or discontinue their operation for some time of the year. So they are not operational 12 months a year, but the mining operations tend to concentrate on the summer month. And if we see that the times during which the mines operate lead to a greater pollution level in the river system, this can, of course, also be interpreted as a sign for a mining origin. So we look now once again at the example of arsenic. And for arsenic, we here look at the basin of the Kara River Basin, one of the subbasins of the Selenga in Mongolia. And when looking at natural background concentrations in the upper catchments that are not affected, not impacted by mining or any other anthropogenic activities, we find a natural background concentration of arsenic of approximately 1.8 micrograms per liter. So anything that we find that would be close to those 1.8 micrograms per liter would have to be considered a geogenic background concentration. But when we move into those tributaries where the gold mining takes place, we can see that the concentrations increase to somewhere between 19 and 43 micrograms per liter, and in between for the gold mining impacted subbasins. The second figure here shows the arsenic concentrations in the Kara River just below a gold mining region. And we can see here the range of concentrations during the summer, winter, and autumn seasons. In this case, the seasons summer 2014 and autumn 2016, where you can see the red asterisk. This refers to a situation where the mining operation was ongoing. And we can see that in these cases, we saw concentrations reaching up to 25, 26 micrograms per liter. Whereas at a time when the mining operation was paused, the concentrations were lower, and the highest ever detected arsenic concentration was about 14 micrograms per liter. Now, when looking at arsenic in the environment, mining is one important source, but it's actually also the usage of products that originate from mining. For arsenic, the very highest concentrations that we found were in ash ponds that are found close to thermal power stations. And in these ash basins, we frequently measured arsenic concentrations exceeding 1,000 micrograms per liter. And the big problem is that these ash basins are very often located in riverine floodplains, as is the case here in Dachan, where this picture was taken. And this, in the end, means that there is a risk of groundwater pollution, potentially also river water pollution. And in this specific example, even some drinking water wells are located nearby. And in the first drinking water wells of Dachan, increasing arsenic concentrations could be observed in recent years. Now, I mentioned the linkages between raw materials extraction and water/soil security. I will now take a look at a second aspect, namely food security and its linkages to water and soil. And when we look at the upper Selenga basin, food and water are, as everywhere in the world, of course, strongly linked. Firstly, irrigation is commonly practiced and increasingly practiced in regions where there is a desire to increase the agricultural yields. The floodplains very often serve as pasture land, so we find high livestock densities very close to the river. And this agricultural land and pasture land is often associated to soil erosion. So there is a sediment transport from these surfaces towards the river system. And we will see later that this sediment input can have problematic consequences for the aquatic ecology of the rivers. But the mobilization of sediments can, in some case, also be something problematic and lead to a bioaccumulation of toxic substances in plants and animals through soils and water. So when we look at the situation of agriculture in Mongolia, we can state that in the post-socialist period, initially, from 1990 to 2006, the land that was cultivated decreased, and only after 2006, some sort of turnaround could be observed. In 2009, the Mongolian government published a national plan for food security, which led to a massive increase in agriculture. And the declared political goal now is actually not only to be self-sufficient in terms of agricultural production, but even to produce for exports. Now, approximately under irrigation, but this fraction is increased. When we look at the relevant net, there is about 4 to 15 per hectare and year for steppe that is not in any way. So we can see I'm very sorry. It appears that there was an interruption in the connection. So I will briefly repeat what I last stated. Agriculture basically has an leads to an increase in surface erosion. So for agricultural land, this is significantly higher than for steppe. It's a several-fold increase in surface erosion.
Your presentation is switched off now. Maybe you can again open the demonstration.
I will. Can you see it now?
Yes.
Good. So yes, as I had just mentioned, the increase in agricultural land in the end leads to an increase in surface erosion, which is several times higher on agricultural land as on uncultivated steppe land. Now, when we look at pasture land, an important development in the recent past is that we can see that following the turn of the millennium, there was a very significant increase in livestock numbers in Mongolia. So today, Mongolia has a livestock population exceeding 70 million, and you can see that from the 1970s to the 1990s, this was somewhere between 20 and 25 millions. So there has been a very strong increasing trend here. And livestock has a considerable impact also on the river system. Soil and riverbank erosion also are increased under the impact of livestock. But there is also an increase in nutrient loads if significant numbers of livestock enter the rivers. And this can, in the end, lead to changes in the aquatic fauna, but actually also aquatic flora. So when we look at sediment and nutrient loading due to livestock, this has an effect on the hyporheic zone in the Mongolian rivers. It mechanically and biologically blocks the function of the hyporheic zone. As you probably all know, this is the zone at the bottom of a river where there is an exchange between the surface and the groundwater, and this zone has several important functions. One is that it's a habitat or refuge for many different aquatic organisms. It plays a very important role, for example, for many fish species to lay their egg, and it plays a very important role for aquatic biodiversity. Now, when looking at the Kara River, some colleagues of mine looked at the changes in the total suspended sediments and the fine sediment fractions. And one thing that we can see is as we move from the upstream to the mid and downstream sections, basically the total suspended sediment concentrations increase more than sevenfold as compared to the upper parts of the river basin. We can see that within this sediment fraction, the fine sediment smaller than 2 micrometers in particle diameter increase from 21.8 to 29.2 micrometers. But we can also see that, for example, when we look at nitrate nitrogen, the concentrations in the upper part of the river basin were so low that we could not even detect them, and this then increased to 0.12 and then ultimately 0.33 milligrams per liter. This is, of course, not only due to impact of livestock contributes to it, but there would also, for example, in a few places be a discharge of urban wastewater, for example. So basically, these changes have an impact on the hyporheic zone in the rivers, and one of the impacts can be seen here. We can see on the left side here sampling sites in the upstream part of the Karthe River, where we can see that when looking, in this case, at the macrosol benthos, we can see a relatively high level of taxa richness, which then increases as the turbidity increases and as the hyporheic zone is increasingly getting blocked. We can see on the second picture here something similar for the percentage of EPT organisms, which are an indicator of the state of the aquatic ecosystem. And we can see that their share really decreases from close to 80% in the upstream parts of the basin to less than 20% in the lower parts of the basin. And even if we looked at different indicators, such as a Shannon index or other metrics, the picture would actually always be the same. And here we can state that this is very strongly linked to the fine sediment influx that we see into the river system. And this is mostly actually is the bioaccumulation. And what we see here is heavy metal bioaccumulations in the liver and muscle. So sorry, once again, I think the connection was lost. I think now you can once again see the screen. We can see different fish species, which are mentioned here on the bottom. And basically what we can see is that there is different species differ in their tendency to bioaccumulate certain trace elements, but we can see that here, for example, zinc, arsenic are bioaccumulated by fish that were caught, and this actually continues. It's not only zinc and arsenic, but here we see a few more elements. Nickel and copper were not found really to be a problem. But here, if we look, for example, at mercury or lead, substantial bioaccumulation of these elements was observed. Whenever you see a dotted line here, this means this is a guideline value for food, particularly for fish, that should not be exceeded. So we can see here in case of lead, and this is marked by these yellow to brown dots, we are not yet exceeding this value, but there is a clear sign that lead is bioaccumulated. So I now come to the end of my presentation, and in summary, we can state that water quality in the Selenga River Basin is in multiple ways connected to raw material extraction, to soil security, and to food security. And when we look at these linkages, we can, for example, state that water security initially is a prerequisite for raw materials extraction, and for food security, we need water in the raw materials sector. We need water as a prerequisite to produce food. We also need soil security is a prerequisite of food security, but unpolluted soils also play an important role for water security. And we can see that there are further linkages that, for example, raw materials such as coal in order to produce energy is a prerequisite for providing maybe safe drinking water or food to the population. So these are positive linkages, but there are also several ways in which negative impacts can work. So, for example, the raw material extraction, as we saw, had a negative impact on water security and soil security in a direct way. But we also saw that food security can have an impact if, for example, we mobilize sediments in the riverbanks, so even food production has an impact. And there are then also indirect effects. So if, for example, soils are polluted due to raw material extraction processes, this can have an indirect effect on water security, so that even more indirect chains develop. Now that the soil has polluted the water, this will have another feedback loop to food security. So we can see the whole system is highly interconnected. And with this, I would like to thank all of you for your attention. For those who wish, you can also see in the end a list of references that I have used for this presentation. So if anyone would like to check up some details later, I would like to offer this to you. And if one of you is interested in finding out more about the activities of United Nations University, it's possible to follow us on all different sorts of social media. It's possible to have a look at our website and to subscribe to a quarterly newsletter. So thank you for your attention, and I'm of course open to answer your questions.
Thanks a lot, Daniel. That's both thanks for excellent talk, and also thanks for coming and for accepting this invitation. I know that's very busy days for you, or the last one, but anyway, and of course the Selenga in Mongolia is always good to learn more about what is going on here. And also, just to the end of your talk, I think it's very could be good if we find some solution to sign some sort of agreement between Moscow State University and United Nations University. As far as I know, you said that it's quite a lot of possible options for collaboration, and that can be very interesting also for young scientists here at our university. And I would go to the questions which we have in the list from the audience. Yes, Daniel, just I see that connection sometimes not good, so I'm afraid if we are losing you. Yes, I see you are moving, then probably it's okay.
Yes, I am here, yes.
Okay, good. So the first question is from Natalia Oleynikova, Hydrochemical Institute, and from Russia. And the question is, what is the share of underground runoff and its possible impact on the formation of the Selenga River water quality?
Once again, please, Sergey.
So the question is about underground runoff, ground runoff. So, and how it can affect the water quality.
Yes.
In the system.
So it definitely has, the ground runoff has a major impact on the surface water quality when we look at the one hand on mining areas, but also, for example, at urban areas where we find quite high levels of soil pollution. This has definitely an effect on the river system. There has not really been, I think, a quantitative investigation at the basin scale, how much this actually contributes.
Okay, thanks. That can be some, I guess, that's really the topic which is not really deeply covered in the region, I guess, yeah. So, and so then there is another maybe comment. I would read it just to confirm that the topic is challenging. So the comment from Mexico. So I'm interested in these topics because in Mexico there are lots of rivers with several erosion problems and sediment transport. So maybe just so general comments, and then I go to the question. The next question is from Dr. Vincent Azuka. So he is wondering about that's the most rainfall in West Africa is highly erosive, culminating to high erodibility of soils. So and transport sediments. So the most intensive rainfalls. And the question, how can this menace be combated on your research? So
yes, so rainfall actually also plays a very significant role. And one thing that I have not mentioned here is that in case of the Selenga River Basin, actually there has been a significant change in the types of rainfall. So in the past, it was typical to have rain events which were rather long-lasting but rather weak events, and there is an increasing trend towards short but very strong rainfall events. And these events actually tend to mobilize far more material than long-lasting but weaker events. So this is one aspect to take into consideration. Second aspect is that I mentioned previously that in dry land such as Mongolia, we can see that a very significant share of the sediment loads in the rivers actually originates from riverbank erosion. So the primary measure to consider is to stabilize or not destabilize the riverbanks. So managing, for example, livestock numbers in the riverbanks, making sure that mining activities are restricted to regions outside the immediate vicinity of the rivers. This really helps a lot to reduce this sediment input into the river system, but also potentially the pollutant input.
Okay, thanks, Daniel. And maybe just as far as we are short in time now, very brief, short question. What would you say the number one in the future water-related research in the Selenga and Baikal Lake catchment?
Yes, I think one aspect that is, of course, a very important one is the question what will happen regarding water diversion projects. There have for a number of years been discussions on diverting water from the Selenga River system to mining operations in the southern part of Mongolia. They have not yet materialized, but there are plans to build dams and to divert water, dams both for hydroelectricity production and for water diversion. And this would have very significant impacts on this system. It would have significant impacts on the hydrology, significant impacts on the aquatic ecology at this moment, we can state that we are actually talking, when we look at everything that's upstream of Lake Baikal, about one of the largest undammed river systems in the world. And this would really change very dramatically if dams were built.